Picture this, a world without batteries. No smartphones, no laptops, no electric cars. How did we go from sparks of static electricity to the tiny energy-packed powerhouses we rely on today? This journey is made just for you to listen to. Whether you're driving, relaxing at home, or on the go, let your imagination spark as we uncover the surprising history and chemistry of batteries.
7 in 49, Benjamin Franklin and the birth of the term battery. Franklin wasn't inventing batteries as we know them today, but he was a curious scientist, experimenting with electricity. His famous work with Leyden jars, a type of glass container used to store static electricity, laid the groundwork for something much bigger. He lined up several of these jars and called them a battery. But why this name? Well, Franklin saw them as a group of objects working together, much like a battalion of cannons firing in battle. However, these weren't real batteries. They couldn't provide a continuous flow of electricity. Instead, they delivered a single, shocking jolt. To move from occasional shocks to a steady supply of power, we needed chemistry to step in and change the game.
1800, Alessandro Volta and the first true battery.
Enter Alessandro Volta, the rock star of electrochemistry. Volta made a groundbreaking discovery by stacking discs of two different metals, zinc and copper, with a salty, wet cloth in between. He created the first ever true battery, the voltaic pile. So, how does it work? Imagine zinc as an eager donor of electrons. It wants to get rid of them. Copper, on the other hand, happily accepts those electrons. The salty cloth, known as the electrolyte, allows tiny charged particles, ions, to move between the metals. This flow of electrons generates an electric current, much like water flowing through a pipe. And just like that, the world had its first continuous power source. Fun fact, Volta's invention was so powerful that Napoleon Bonaparte himself awarded him a medal.
1836, the Daniell Cell, a more reliable battery, but there was a problem with Volta's design. It didn't last long. The reaction caused a buildup of hydrogen bubbles, which stopped the battery from working.
Picture two metal plates, zinc and copper, each placed in its own beaker. Zinc in zinc sulfate, copper in copper sulfate. This setup fixed the problem of gas bubbles that caused older batteries to fail. Electricity is all about moving electrons. Zinc wants to get rid of its electrons, so it dissolves into the solution as zinc ions, causing the zinc plate to shrink. These electrons can't just vanish, so they race through a wire, traveling toward the copper plate. This movement creates electricity, the power that could send telegraph messages across continents. At the copper plate, copper ions grab the electrons and turn into solid copper, thickening the copper plate. This whole process is a redox reaction. Oxidation is losing electrons, oil, and reduction is gaining electrons. Zinc loses electrons, copper gains them, and the flow of electrons powers the device. So in simple terms, zinc dissolves away, electrons race through the wire, copper grows, and you get steady electricity. Thanks to Daniell's clever design, the Daniell Cell powered long-distance telegraphs and revolutionized communication.
1859, Gaston Planté and the first rechargeable battery. What if we could make a battery that didn't run out after just one use? In 1859, French scientist Gaston Planté cracked this puzzle with the invention of the lead-acid battery, the world's first rechargeable battery.
Inside a lead-acid battery, there are two plates, one made of lead, the other of lead dioxide, both immersed in sulfuric acid, which acts as the electrolyte. When the battery is in use, the acid reacts with the plates, creating lead sulfate and releasing electricity. Over time, the plates become coated with lead sulfate and the reaction slows down, like a car running out of fuel. Here's the magic. When you plug the battery into a charger, the electricity reverses the reaction, dissolving the lead sulfate and returning the plates to lead and lead dioxide. This restores the battery's power, ready to deliver electricity again. Next time you start your car, remember, you're using 1859 technology. Lead-acid batteries may be old, but they're still in use today because they're reliable, inexpensive, and pack a powerful punch.
Ever heard of those classic AA or right AA batteries? Their ancestor was invented in 1866 by Georges Leclanché. He created the carbon-zinc battery, which was much safer and more convenient than the older, liquid-filled designs that came before it. This was a pivotal moment in the history of portable power.
The Carbon-Zinc battery featured a zinc case that acted as the negative electrode, anode, and manganese dioxide, MnO2, as the positive electrode, cathode. These electrodes were separated by a paste of ammonium chloride, which acted as the electrolyte, allowing ions to move between the electrodes. When the battery is in use, zinc at the anode undergoes oxidation, losing electrons, and dissolves into the electrolyte as zinc ions, creating an electron flow that powers devices. Meanwhile, at the cathode, manganese dioxide, MnO2, gains electrons in a reduction reaction, completing the circuit and allowing the battery to deliver power.
However, there was still a significant issue with older batteries. They often leaked. In 1888, Carl Gassner addressed this by improving the carbon-zinc battery design, turning the liquid electrolyte into a paste and creating the dry cell battery. This development made batteries much safer by eliminating the risk of corrosive leaks and allowed them to be more portable and durable.
In 1899, Waldemar Jungner revolutionized energy storage with the invention of the nickel-cadmium. The battery works by using nickel oxide hydroxide at the positive electrode, which reacts with water and electrons to form nickel hydroxide. At the negative electrode, cadmium reacts with hydroxide ions, losing electrons and turning into cadmium hydroxide. This movement of electrons provides power to devices. The real magic lies in its rechargeability. When plugged in, the reactions reverse, restoring the battery's original state, ready for more use.
However, cadmium's toxicity led scientists to seek safer, alternative battery technologies. Despite this, nickel-cadmium batteries paved the way for modern rechargeable power. In the 1950s, a major leap forward in battery technology changed the way we powered our devices. The Alkaline battery, developed by Lewis Urry, replaced the older zinc-carbon batteries and offered a much longer lifespan, sometimes lasting for months or even years. So what made the alkaline battery so special?
The key innovation was in the alkaline electrolyte. Unlike older batteries with acidic solutions, Urry's design used a basic electrolyte, usually potassium hydroxide. With this setup, zinc at the anode undergoes oxidation, losing electrons, and manganese dioxide at the cathode undergoes reduction, gaining electrons. The alkaline electrolyte makes these reactions more stable, so the battery lasts much longer. Thanks to the stable alkaline electrolyte, the battery avoids corrosion and keeps its charge for months, unlike older designs that quickly degraded. The alkaline battery is like the tortoise in the race. It's steady, reliable, and lasts in the long run. This breakthrough powered a whole new era. From Game Boys to smoke detectors, the alkaline battery quietly revolutionized modern life.
All right, here we are. Stepping into the 1990s, a decade of technological breakthroughs, and we finally reached one of the most transformative inventions of the modern age, the lithium-ion battery. In 1991, Sony brought this wonder battery to the consumer world, and it changed the game. No more bulky, heavy batteries draining our devices in hours. Lithium-ion was a whole new ballgame. But what exactly made this battery so special? Let's dive in.
So, what's the secret behind lithium-ion batteries? It all comes down to the materials and the way they work. Imagine trying to fit all the power your smartphone needs into a small, sleek package. Sounds impossible, right? But lithium is here to save the day. It's the lightest metal on the periodic table, lighter than even water, making it perfect for storing a lot of energy in a compact, portable form. Inside the battery, there are two electrodes, lithium cobalt oxide, positive, and graphite, negative, separated by an electrolyte. When you charge your device, lithium ions move from the positive to the negative side, storing energy. When you use the device, the ions return to the positive side, releasing energy and powering your device. This back and forth movement allows the battery to charge and discharge efficiently, giving it high energy density. Lots of power in a small, lightweight package. This cycle allows lithium-ion batteries to last for thousands of charge cycles, making them perfect for smartphones, laptops, and even electric cars. Today, beyond the original lithium cobalt oxide batteries, we also have NMC, nickel manganese cobalt, and Ca, nickel cobalt aluminum batteries, which are more durable and efficient, powering everything from phones to electric vehicles.
From Volta's metal plates to today's lithium cells, the battery has come a long way. But the journey isn't over. Scientists are exploring solid-state sodium-ion and even biobatteries that could power the future without rare metals. So next time you plug in your phone, remember the innovation behind it. If you enjoyed this, subscribe, like, and stay tuned for more electrifying podcasts.